Okay, this is lecture 17, chapter 9, and this lecture is a little different in that I'm not using PowerPoint because the concepts are easier to cover if I just simply draw them as if I were in a lecture with a whiteboard. So I'll just be doing the same thing only with a pad of paper. So far you've hopefully understand the concept of centers of mass, centers of gravity, center of area. And so this is an extension to that. The moment of inertia is simply a resistance to bending or resistance to rotation about a particular axis. So I always start off with a little example is imagine you're trying to cross a creek and you have a piece of wood and you don't want to get wet. So you decide, how are you going to lay that piece of wood across the creek? It's a 2 by 12, so 2 inches thick, 12 inches wide. Not truly 2 by 12, but that's another story. So are you going to lay it flat like most people would? And so so you have more space to actually walk across? Or are you going to stand it on its end so that the 12-inch, you have to essentially balance yourself on the 2-inch width side? So now, obviously, it's easier to walk across if it's laid flat, so to speak, with the 2-inch side being thickness versus the 12-inch being thickness. What we want to know is which one's going to deflect more based on the load. Now, both have the same mass, same dimensions, and so your intuitive answer is probably going to be this one if we lay it like this. So if we go ahead and put a load on it, we're going to get something that's going to look, this again is a little exaggerated, it's going to look more like that, where we have a load in the middle, we have it supported on both ends, and it ends up deflecting. If we try to do the same thing with this, the deflection is going to be much, much smaller. Now, the reason for that is that this board has a larger moment of inertia. And I'll refer to that as the MOI most of the time. All right. So let's think about what is the moment of inertia. Imagine, let's take another step, and let's say you have a board. Let me go ahead and draw that real quick. So here's our beam. So imagine I've taken a beam, kind of like the 2 by 12, but let's say it's thicker. Maybe it's 12 inches tall and 6 inches wide. So it's a very large beam. And the idea of the beam is that it's going to support a load. Now, we apply a moment to the beam, and this is referred to oftentimes as a bending moment. And so you can see that the bending moment comes from the fact that what do we have? We have force here, force there. Well, that creates, as we know, a couple, which is also can be called a moment. Now, if you think about it, that the way the force is drawn here is a result of loading the beam in the center and then supporting it on either end. And so what we end up with is if we were to put a y and an x-axis on here, and we were to look at the stress along the y-axis starting from the top and working its way down to the bottom. Now remember, stress is equal to force over area. And so what we would get if we were looking at y, if we plotted y versus stress, we would get something that looked like this. And so what this would represent is this location here is that, according to y, would be right here at the top. So that would be right at the top. And then down here would be, say, right at the bottom. Say that's the bottom. Now, the reason this has the shape it does is when you bend something like this, then think of it as like your hand. It's hard to do on video, but if you take your hand, and it's easier if I can't really do it with my hand, but take your right hand and cup it. So do this. So when you cup it, you're effectively making the shape like this. And you notice that when you do that and you cup your hand, the skin in your palm compresses and the skin on the back of your hand is in tension, is pulled. That's the same thing that happens on this beam. When the beam deflects, because of the way this is loaded, you get a compressive stress on the top. And as you travel down through the beam until you hit the middle, then in this case it'd be the geometric middle, you get basically the stress falls to zero. This stress is called the neutral axis. That's because there's no stress at all. And if you keep going, you end up down here at the maximum tensile stress. And so typically when we talk about stress, we know that positive stress by convention is tensile stress. Negative stress over here is compressive stress. So why do we care? So how does this relate? Well, we have this equation where we can say stress is equal to, if we want to calculate it, it would be m times y all over I. There's a negative sign there. And what that tells me is that m is the bending moment in foot-pounds, y is the location from here anywhere along this, and this number here is I, and that is our calculated moment of inertia. And what you can see from this equation is that if the moment of inertia is large for a given bending moment, the stress is small. And that's good because the stress is what's going to determine whether the material yields or not. So if you think about material and you have a typical tensile test, stress versus strain, you know that it goes something like this, and then it reaches a point which is called the yield point. There's a little transition, and depending on the crystal structure, it'll keep going. This transition is based on crystal structure, but they all pretty much look the same. They reach a peak stress, which is your ultimate tensile stress, and then there's fracture. But pretty much anything over here is where, as an engineer, you're going to work, because you only care about material until it's, or you only want to design to a point where you never exceed this yield point where you have permanent deformation. So if I can increase my moment of inertia of my beam, then I can reduce the stress, and because I may not be able to control the bending moment based on how the structure is built. Now this is getting way beyond the concept of statics, but I'm introducing this because you will see this if you take CE 204, this is where you'll start with. So the main interest we have, and by the way, the negative sign is because if you travel in the positive y direction, then you get a negative stress, which makes sense because it's compressive. And if you travel in the negative y direction, the negatives cancel and you get a positive stress. Anyway, so we're going to focus on calculating this number here. Now its applications is beyond the scope of the class, but we want to know how do we get I? What is I? Now it turns out that I can be calculated by either integration, or it can be, or you can use equations for typical geometric shapes, very similar to what you did with centroids. So one thing we want to address, though, is you may recall in the reading from the centroids is that this relationship Qx is equal to y bar times A, and Qy was equal to x bar times A. And this was called the first moment of area. And then we had what's called the second moment of area, and that's the moment of inertia. So the second moment of area is equal to essentially the integral of this Qx. And so that's where, or essentially the gives us I. Okay. So oftentimes what we'll see written is we'll see written d derivative ix equals, in this case, y squared dA. So you may remember that in the first, when we're finding the centroid, remember x bar was the integral of y dA. So now we have the integral of y squared dA. So first moment of area, we use this. Second moment of area, moment of inertia, we use this. So I'm not gonna focus on integration techniques. I mainly am showing you this just to give you the background. The problems that we'll do will be composites. But if we look at a simple example, and this works the same for IY, so we can also write DIY equals the integral of x squared dA. So look at just a simple example. Let's say we have, here is our x-axis, here is our y-axis, and let's say we want to know the moment of inertia of a rectangle. So we know that the base is B, we have a height h, and we know that if we take a little strip, a little sliver of area, we can call that dA. But we know that what is dA? It's equal to B dy. Basically the base times a little sliver of dy. So knowing that dA equals B dy, and knowing that dIx equals integral of y squared dy, then what we can do, y squared dA, is what we can do is we can take this relationship and we can substitute this in down here for dA, so we get dIx equals the integral of y squared times b dy. So all I did was take this b dy, put it in for dA, and I have that. So now I can integrate with respect to y, and when I do that, and I go from 0 to h, what I get is b y cubed, because b is a constant, divided by 3, the value will move from 0 to h. Or that gives me 1/3 bh cubed. So what that says is that the moment of inertia of a rectangle from its base, so if I take it with respect to the base, then that moment of inertia for that is 1/3 bh cubed. All right. So let's imagine that here's the center, and again, we're calling this the base and this the height. So it does depend on your orientation. So in this case, because we're taking this about the x-axis, so Ix, meaning moment of inertia about the x-axis, equals 1/3 bh cubed. Now, if we took this same shape and did this to it, right, just flipped it, turned it 90 degrees, then this would suddenly become b, and this would be h by our convention, and this equation would change. It would become 1/3 hb cubed. But usually what we do is we change the, we want to make sure that we always use the base, we always want to use the, whatever this distance is, that's the height relative to the height of the, backing up, let me back up again. We always want to make sure that we use whatever this perpendicular distance is as our height in this, because you notice that it makes a big difference if you have which one you cube. So what this says is that the height, how high it is going to make a big impact in the moment of inertia compared to its base. So the farther you get away from the axis, the more material you get away from the axis of rotation, the bigger this number is going to be. So this is a number that you could look up, and what we'll find is that if you look up, you would also get about the center. If you want to know I here, x, about the center, it would be equal to 1/12 dh cubed. Because if you're rotating about the center, it's not going to be as great a number as that. And I'll show you how that was derived in a second. Now I want to continue this discussion. The last couple of minutes I don't think could have been as clear as possible. So I wanted to reiterate this, and I should have written this as cubed, sorry. So it's not H, it's not an H3 compound. So you have, now what I've done here is I've showed you here, so here's my rectangle. And as I mentioned, if you're taking moment inertia about the base, it's 1/3 bh cubed. If you're doing about the center, it's 1/12 bh cubed. Most of the time, when you look on a table like the one in your book, which is on, I think, page 500, 501, what you'll find is the moment of inertia is usually referenced by the centroid. Now, the reason for that is that if you want the moment of inertia and you're using a calculation, very rarely are you going to be using a single shape for one, or are you going to know that the axis of rotation is going to necessarily be right at the centroid. So what you have is what's called the parallel axis theorem. And this is just, a simple equation that allows you to calculate the moment of inertia from any axis that's parallel to the centroid axis. And there's ways to do it with mechanics, but that's way beyond the scope of what we're doing. But let's look at this example again. So we have X bar, and usually the notation of the centroid is a little bar, either a bar above and a apostrophe or a dash, and whereas a normal axis just means any random axis. So the equation says that for a moment of inertia about any x-axis, that's going to equal the moment of inertia about the centroid plus AD squared, where A is the area of the shape, so we'll call it base times height, and D is the distance between the two axes. So let's use this to see where we got this from. So we know, let's say we looked up in our book and we know that Ix prime is 1/12 BH cubed. So if we add the AD squared to this, we know that the area of this is base times height. What is the distance? Well, if the distance between here and here is height over 2. So h over 2 squared. So what does that give me? That gives me 1/12 BH cubed plus, and what is this? This is going to be 1/4 BH cubed. So if I convert this, this is going to be 3/12 plus 1/12 is 4/12. What is 4/12? It's 1/3. So that's where I get the 1/3 BH cubed. So let's do a quick example showing how you might use that in practice. So in this example, you have just a simple box that's 1 foot by 1 foot. And we're going to say that here's the center, and we're interested in finding the moment of inertia about this axis down here. So we know that the distance between here and here is 24 inches. So we want to know what is that moment of inertia. All right. So we know that for a square or rectangle that Ix prime is just, again, 112 BH cubed. And so we can calculate that. Now we know that because we're using the parallel axis theorem, we know that this 1x, we'll just leave it as an x and say, not 1x, I'm sorry, Ix, moment of inertia, equals, and that's for this axis, let's first write it Ix prime plus 80 squared, which equals 112 BH cubed plus AD squared. So we just have to add these two together. So let's first do this. So 112 BH cubed. So that's going to be, we know that this is 1 foot by 1 foot. We're going to stick with inches. So it's 12 by 12. So essentially we have Ix prime equals 112 times 12 times 12 cubed, right? So 12's cancel, 12 cubed equals 1728. Now the units are inches to the fourth. And so moment of inertia is always whatever unit to the fourth. You can see that because you're multiplying base times height cubed. They're always going to be inches to the fourth. And that works out in that equation I showed you earlier, where you have moment times distance divided by moment of inertia. That will give you the units of stress. Anyway, so we have that value. So we know that just this box in space has a moment of inertia, resistance to rotation of 1720 inches to the fourth. Don't worry so much at this point about what that means in the bigger picture. For now, we're just trying to calculate it. And unfortunately, we won't really go beyond this. You're going to have to wait till CE204 before you really use it. But you will use mass moment of inertia in dynamics. So that gives you hope. Now let's look at what is the effect of having it moved away 24 inches. So we also have this AD squared term, which we know is going to be area. So area is going to be 12 by 12. So 12 squared. And then times d squared, so 24 squared. And so if we calculate that, we have essentially, we have 144 times 24 squared, which I believe is 576. And then multiply those together, we get 82,944 inches to the fourth. So notice how much more moment of inertia is added from this little bit to this just by moving it. And we didn't move it that far in the scheme of things. This is 12 by 12. We moved it 2 feet. So it's not really that big a deal. But that's the reason, and because of that power of the moment of inertia rising, that's the reason why when you look at an I-beam or something in a large structure, that the I-beam looks like this. And we'll do some examples with an I-beam, but I-beam has a shape like that. And normally the center is the neutral axis. And then of course the thing's gonna bend based on the moment applied. But the whole idea with this is that if you get more of the material away from the neutral axis, this moment, this I is going to get really large. So one other thing to remember is that if you have a bending moment, we usually write them like this, where you have a load here, it's that. But generally, you leave these supports out and you just draw it with the bending moment. This is what's considered a positive bending moment. And if you have a bending moment that looks like this, where it's bent out like that, that's considered a negative bending moment. Now, in other countries, I think in Australia, it's the opposite, but in America, we use this convention. And you can always remember because this bending moment's smiling, so it's positive. This bending moment's frowning, so it's negative, okay? All right, so that is a quick introduction to moment of inertia. And there is information in your book on that, but I wanted to get this as the next lecture. In the following lecture, I'm going to do examples of how to do these problems using the table. And after you do a few examples, you'll see that it's really not that difficult. And again, you'll have to wait until C204 to really see how this is applied and how you use it. All right, thank you.